In the last lecture, we were examining the thermal conductivity of a composite consisting of a matrix of conductivity Km containing within it spherical inclusions, particles with thermal conductivity Kp. And this was the z axis. Okay. Length was L. Okay. And across that length L, we had applied a temperature difference delta T. You had particles in a matrix. Okay. The particle had radius r. Okay. The temperature field far from the particle was a linear temperature field. Okay. T is equal to T prime times Z. Okay. And I had told you that you can add a constant temperature, it makes no difference as far as the flux was concerned. The particle conductivity, thermal conductivity is Kp, matrix thermal conductivity is Km. Okay, the particle thermal conductivity is Kp, matrix thermal conductivity is Km, and this T prime is basically equal to the difference in temperature divided by L times Z. Okay, that is the temperature gradient far from the particle. There is going to be a disturbance to the particle temperature due to the presence of the particle. Okay, and that we had analyzed in a spherical coordinate system in which r was the radial coordinate and theta is the azimuthal angle made by the radius vector with the z direction. There is no variation in the meridional phi direction. Okay, there is no variation in the meridional phi direction. We had done a calculation of the conductivity in the particle in order to find out what is the effective thermal conductivity of the form Q average is equal to minus K effective times delta T by L is equal to minus K effective times T prime. Okay. So, what we wanted to find out was how is this K effective related to the particle and matrix thermal conductivities and the particle volume fraction in the dilute limit where the temperature field around one particle does not affect the where the temperature disturbance due to one particle does not affect the temperature field around another particle. So, that the particles can each be considered to be a spherical inclusion in a linear temperature gradient far from the particle, because there is no disturbance to the temperature field at this particle due to the presence of other particles. As we will see, that is valid only in the limit of small volume fraction or when the distance between the particles is much larger than the particle radius. So, in this coordinate system we had to solve the heat conduction equation. Okay, del square temperature in the particle is equal to 0, del square temperature in the matrix is equal to 0, okay, with the boundary condition as r goes to infinity, T matrix is equal to T prime Z. Okay. Linear temperature gradient far from the particle. Okay. T is equal Tm is equal to T prime Z, which is the same as T prime r cos theta. Okay. And that r is equal to r. The particle temperature is equal to the matrix temperature. Flux perpendicular to the surface has to be equal in the particle and the matrix. Okay. So, those are the boundary conditions. Of course, at the center of the particle we require that the temperature has to be finite, it cannot go to infinity, okay, at the center of the particle. Okay. So, this solution del square T equal to 0 in a spherical coordinate system 1 by r square d by dr of r square partial t by partial r plus 1 by r square sine theta partial by partial theta of sine theta partial t by partial theta is equal to 0. Okay. Separation of variables, t is equal to f of r g of theta. Substitute, divide throughout by f times g, and in this case multiply throughout by r square, and you will get 1 by f d by dr of r square df by dr plus 1 by g sine theta is equal to 0. And I had done a series solution in order to demonstrate to you that both of these terms on the left side, the first and the second term, first term is only a function of r, second only a function of theta, both have to be constants of equal in magnitude and opposite in sign. The solution for g is finite, okay, at theta is equal to 0 or theta is equal to pi, only if this is of the form n into n plus 1. I had shown you that by a series solution, okay. Only if this is of the form n into n plus 1 where n is an integer, only then is the solution finite, okay, in the theta direction, which means that this has to be equal to minus n into n plus 1. Okay. And we solved these separately to get equations for the particle and for the matrix. In both cases, the temperature field has the same form. This solution is of the form, okay, T is equal to sum n is equal to 0 to infinity a r power n plus b by r power n plus 1 Pn of cos theta. Okay. Therefore, the particle and the matrix temperatures are both of the same form. T particle is equal to sigma n is equal to 0 to infinity of a, I am sorry, it should be a n here because each of these coefficients has to be different. Okay. A n particle r power n plus b n particle by r power n plus 1 into Pn of cos theta, okay, and T matrix is equal to summation n is equal to 0 to infinity of a n matrix r power n plus b n matrix by r power n plus 1 Pn of cos theta. And the boundary conditions are, as the temperatures are equal, minus Kp partial Tp by partial r, the fluxes perpendicular to the surface are equal. And as r goes to infinity, T in the matrix is equal to T prime z is equal to T prime r into P1 of cos theta, because P1 of cos theta is equal to cos theta itself. So, that is the temperature as r goes to infinity. Since there is forcing only proportional to P1, there is no forcing proportional to P0, P2, P4, P3, P4, etc. There is forcing only proportional to P1. Okay. The temperature at infinity for the terms proportional to, if I expand out the boundary condition at r going to infinity in a series in the Legendre polynomials, the terms proportional to P0, P2, P3, etc. are all 0. And because the boundary conditions are equality of temperature and flux, you will find that all the coefficients are all 0 for the terms proportional to P0, P2, P3, etc. The only non-zero term is only due to P1. Therefore, the solution for the temperature field contains only terms proportional to P1 of cos theta. That is because all the Legendre polynomials are all orthogonal to each other. Okay. They do not when you multiply two different Legendre polynomials you get 0. Okay. So, because of that the only solution you get is proportional to p1 of cos theta. Okay. So that the orthogonality of the Legendre polynomials and the fact that as r goes to infinity the temperature is proportional to p1 of cos theta implies that the only term in the series is for n is equal to 1. Okay. The only surviving term in the series is for n is equal to 1. Okay. So, I can remove the summations here, okay, and substitute n is equal to 1 in all of these terms. Okay. In the particle the temperature has to be finite at the origin and therefore, this term goes to 0. In the matrix this boundary condition implies that A1 m is equal to T prime. Okay. So, this term is just equal to T prime. Okay. And from these two boundary conditions we can find out what is A1 A1p and B1m. Okay. The solutions we get are of the form, okay, T in the particle is equal to 3 T prime r cos theta by 2 plus k r, and the matrix temperature is equal to T prime into r plus 1 minus k r r cubed, okay, by 2 plus k r into r square into cos theta. Okay. Cos theta is the same as P1 of cos theta. So, these are the two temperature fields. Okay. I can write this alternatively as T prime r cos theta is just z. Okay. R cos theta is just z. Okay. And the second term has r cos theta which is z plus this additional term, the temperature disturbance due to the presence of the particle. We had verified that these temperature disturbances go to 0 when Kr is equal to 1 or the conductivities are equal. In that case you should get equal conductivities on both sides and therefore, the temperature disturbance has to be 0. Okay. Now, from this calculation for a single particle we were trying to find out the average flux. Okay. The average flux in the z direction q average is equal to okay, if we take a volume average 1 over v integral dv of minus k partial t by partial z. Okay. This consists of two parts, the particles plus the matrix. Okay. So, I can write it out expanded in terms of the two parts as is equal to 1 over v integral dv over the matrix of minus km, okay, partial t by partial z plus integral over the particles of dv of minus kp partial t p by partial z. Okay, this is the matrix. Okay. This second term, okay, this second term I will just rewrite a little bit. Okay. So, this I will rewrite it as is equal to 1 over v into integral dv over the matrix of minus km partial t by partial z, okay, plus integral over the particles of dV of minus Km partial t by partial z, okay, plus integral over the particles of dV of minus of Kp minus Km, okay, partial t by partial z. Okay. So, I have written it as the sum of two terms, integral over the particles of minus Km plus integral over the particles of minus of Kp minus Km. You add these two together, you just get integral over the particles of minus Kp times partial t by partial z. Okay. So, I have just written minus Kp as minus Km plus minus of Kp minus Km. Okay. So, that is the only thing I have done. This first term here is the integral over the matrix of minus Km dt dz plus the integral over the particles of minus Km dt dz. So, this is 1 over V integral over the entire volume, okay, of dV into minus Km dt by dz, okay, minus the integral over the particles alone of dV of minus of Kp minus Km, okay, partial t by partial z. So, one we have it over an integral over the matrix, the second we have an integral over the particles alone. That particle integral has been divided into two parts, and when I that is integral of minus Km times partial t by partial z minus of Kp minus Km partial t by partial z. Okay. And these first two terms here are an integral over the entire volume. Okay. So, therefore, I have 1 over V integral dV, or I can take the minus Km out, okay, minus Km integral over the volume of partial t by partial z, okay, minus 1 over V, I am sorry, this should be plus, okay, this should be plus 1 over V integral dV of minus of Kp minus Km dt by dz. This is the second integral is only over the particles. Examine the first term here, minus Km times the integral over the volume of dt by dz. This is the volume integral of the temperature gradient itself. Okay, this is the volume integral of the temperature gradient itself. This volume integral of the temperature gradient has to be equal to the applied temperature gradient, okay, that is delta T by L, because when I integrate the temperature gradient over the entire volume, I should get the applied temperature gradient. Okay. So, this becomes minus Km times T prime, okay, or minus Km times delta T by delta Z, plus this, or if I take the minus sign outside, I will get minus 1 over V integral over the particles of dV of Kp minus Km, okay, dt by dz. The second one is only over the particles. Okay. This is over all n particles, okay, the integral of the flux over all of the particles. We are considering this in the dilute limit, where the temperature field around one particle does not affect the temperature at another particle. Therefore, I can write this as number of particles by volume, or integral of the volume over one particle of Kp minus Km dt by dz. Okay. Kp minus Km dt by dz times the integral over one particle, where n is number of particles. Okay. Integral over n particles is n times the integral over one particle. Okay. This is the average flux, Q average. Okay. And for this integral over one particle, we can find that out from the particle temperature field. Okay. Recall that the temperature field of the particle was equal to three T prime Z by 2 plus Kr. Okay. Recall that the temperature field around the particle was equal to 3 T prime Z by 2 plus Kr. This implies that dTp by dZ is equal to 3 T prime by 2 plus Kr. Okay. That is, the temperature gradient within the particle is just a constant. Okay. Since the temperature in the particle is proportional to Z, the temperature gradient is a constant, and that would have been obvious in the flux lines that I drew for you throughout. Okay. You can see that these lines are straight lines when they go through the particle. That is because the temperature is a linear function of distance Z, therefore, the lines are constants. Okay. They are all pointing in the same direction. Okay. So, this expression for the flux within the particle I can substitute here. Okay. Is equal to minus Km T prime minus n by V integral over one particle dV of Kp minus Km into 3 T prime by 2 plus Kr. This is a constant. Okay. This is a constant. Therefore, the integral over the volume is just equal to the constant times the volume. Okay. Since this is a constant, the integral over the volume is just equal to the constant times the volume. Okay. So, I will get minus Km T prime minus n times the volume of the particle divided by the total volume. Okay. Since the temperature gradient is a constant, the integral is just the volume of the particle times that constant into Kp minus Km, okay, into 3 T prime by 2 plus Kr. Okay. You can see I can take a factor of minus Km into T prime out. Okay. The first term is just equal to 1. The next term is equal to n Vp by V into Kp minus Km by Km, okay, into 3 T prime by 2 plus Kr. So, Kp by Km is equal to 1. Okay. So, I am sure there should be no T prime here, I have taken that out. Okay. So, 3 by 2 plus Kr. Okay. So, this is equal to minus Km into T prime into 1 plus number of particles times the volume of each particle divided by the total volume. Okay. Number of particles times the volume of each particle divided by the total volume is the volume fraction of the particles. Okay. The volume fraction, okay, of the particles. Okay. Is equal to number of particles times the volume of each particle divided by the total volume. Okay. So, this will be the volume fraction times Kr minus 1 into 3 by 2 plus Kr. Okay. So, I can write this as minus Km T prime 1 plus 3 into Kr minus 1 phi by 2 plus Kr. We had wanted to get an effective thermal conductivity as minus K effective times T prime. Okay. We had wanted to get an effective thermal conductivity as minus K effective times T prime. This gives us the effective thermal conductivity. Where Kr, so I am sorry, I should have a Km outside. Is equal to K particle by K matrix. So, this is the effective thermal conductivity of the composite material in the dilute limit when the volume fraction is small and the temperature field around one particle does not cause a disturbance to the temperature field around the other particle. The correction to the temperature due to the presence of particles is proportional to the volume fraction itself. The correction to the temperature to the thermal conductivity due to presence of particles is proportional to the volume fraction in this limit. It is also proportional to Kr minus 1. Okay. That means that the correction to the thermal conductivity, that is the difference between the effective conductivity and the matrix conductivity, the difference between the effective conductivity and the matrix conductivity is positive if Kr is greater than 1 or the particle conductivity is higher than the matrix conductivity. In the opposite case, where the particle conductivity is smaller than the matrix conductivity, the correction to the conductivity due to the presence of the particles is negative. So, the composite effective conductivity is smaller than the matrix thermal conductivity. Okay. So, this is an example of how we use separation of variables, spherical harmonics, the orthogonality relation between the Legendre polynomials and volume averaging in order to find out the effective thermal conductivity of a composite material with spherical particle inclusions. Note that this is dependent only on the volume fraction. It does not depend upon the particle radius. Okay. It does depend upon the relative conductivity and the volume fraction. It does not depend upon the particle radius. So, whether you have small particles or large particles, you get the same effective conductivity, so long as the volume fraction is the same and the relative conductivity is the same. Okay. So, it depends only on the volume fraction, not on the number of particles. Okay. Of course, this calculation is valid only in the dilute limit. As the system becomes more concentrated, there will be an interaction between the disturbances due to the there will be an interaction there will be an effect of an interaction between the disturbance to the temperature fields between nearby particles. Okay. And in that case, you will have to include that interaction as well when you calculate the thermal conductivity. Okay. So, this illustrates how we use solution of the diffusion equation in a spherical coordinate system in order to calculate the correction to the thermal conductivity due to spherical inclusions in a matrix. What we have done so far is only for an axisymmetric system, where there is no variation in the phi direction. What happens if there is a variation in the phi direction and the configuration is not axisymmetric? There will be a modification to these solutions that we will continue in the next lecture. I will see you then.